Good afternoon, everyone, and welcome to the first online training organized by the Heat4Cool project. So today we would like to give you some insights about the Heat4Cool systems, how the technologies are coupled and how they are running in the 4 European demo sites. I would like to share with you the agenda for today's event. I'm Serena Scotton and I'm working for the European Heat Pump Association. After this welcome speech, we will have a presentation made by the project coordinator, Paolo Zancanella. Then we will proceed with 3 sessions. One presenting the project technologies. Unfortunately, we are missing one speaker that couldn't join us today, and he had to present our solar PV and solar thermal technologies. However, we will be able to get some of the information when we will discuss about the demo set implementation. Then we will proceed with the second session that is about the demo set presentation. And then we will conclude the event with a session dedicated to the questions raised by the audience. With this regard, during the event, if you have any questions for the speakers, please use the chat and send a message only to the organizer, that will be me, so I can collect all your questions that will be addressed later on at the end of the event. I inform you that this event, like this webinar, online training, will be recorded to be later on shared as for dissemination scope in the Heat4Cool website. This is it. So I would like to officially start the online training and giving the floor to the first speaker, that is the project coordinator, Paolo Zancanella. Please, Paolo,
Hello,
the floor
everyone.
is yours.
Yeah, hi. Thank you, Serena. So, yeah, thank you, everyone. My name is Paolo Zancanella, and I work for the Politecnico di Milano Department of Energy. I am managing the Heat4Cool project, and today I will briefly provide you an overview on the Heat4Cool project, as well as illustrate what are the main objectives of it. Okay, yeah, thank you. So the Heat4Cool project is an Horizon 2020 project funded by the EU, which has EU funding contribution of up to 5.4 million euros, and it has a duration of 52 months. This was initially 48 months, but due to the current COVID-19 situation, we had to request a 4 months extension. The period covered is from October 2016 to February 2021, and our consortium is made of 13 partners. 9 of those are coming from EU member states and 1 from Switzerland. We have 4 demo sites located in Spain, in Valencia, in Chorzów in Poland, 1 in Budapest in Hungary, and 1 in Sofia in Bulgaria. We Politecnico di Milano are the project coordinator of the Heat4Cool. So just to give you a snapshot of the Heat4Cool consortium, as I said, we are 13 partners, and 3 of them are manufacturing SMEs. So these are basically the partners bringing their actual technology, their product to the Heat4Cool project. So one of them is represented by our German partner Fahrenheit, the heat pump manufacturer that provides the thermally driven adsorption heat to the pilot site in Spain. We have AES Solar. There's a bit of delay with it. Yeah, that provides the solar thermal and photovoltaic technology in all the 3 pilot sites. Then we have Sunamp, the Scottish partner, that provides the heat batteries in 2 of the 3 demo sites. Then we also have 6 engineering SMEs, and these are 4 of those are the pilot managers of the demo sites. So one of them is Thermovat, which manage and develop the wastewater heat recovery system district level in the 3 buildings in Budapest. And we have just a second, yeah, Similec, which is the pilot site of Valencia, the pilot site manager of the Valencia demo. And then we have Sunamp, which is the pilot site of the Hozov demo, Balkanica, which managed the Sofia demo site. And then we have 2 more engineering companies. One of them is Vattenfall that provides the know-how and support at the 3 demo sites for the remote control of the systems and the implementation and application of the CBAMs. Yeah, and then we have Solintel. So Solintel, in the context of the Heat4Cool project, develop the business plan for the exploitation of the results and also develop marketing strategies for the heating and cooling solutions developed in the Heat4Cool projects. So then we have 3 academia research institutions and entities. One of them is us, Politecnico di Milano. We provide the technical, scientific, and administrative support to the project. Then we have the Hochschule Lucerne that provides mainly involved in the development of the designer planner tool. And then we have Tecnalia. Tecnalia is a really key partner for the testing of the technologies that were later on implemented at demo site level, and also provided the cubic facility located in Bilbao, where all the heating and cooling energy efficient technologies were tested before being commissioned at demo site level. Then we have one industry association, which is represented by the European Heat Pump Association, and is the VP leader of the communication and all the dissemination of the all project results. Okay, yeah. So in these slides, I'm going to show you what are the main objectives of the project. So here, the first 3 are the focus of the main objectives of the projects, and then we have obviously some more that I added. So the first of all is to successfully demonstrate that these energy efficient integrated and heating and cooling solutions for building retrofitting are also cost effective and also are easy to be installed. Secondly is to achieve between 20 and 30% energy savings compared to pre-retrofitting status, and also to achieve the payback period of 10 years or close to 10 years. We also have, we also have an objective to show and demonstrate replicability potentials of the Heat4Cool technologies, both at residential and building and district level, and also to identify some target groups in the market that could be potentially be interested in our project and the technologies implemented in our project. Another objective is to develop business models to support the commercialization of each individual project results. And our aim is, of course, to support the EU energy efficiency policies and promote the NZEBs. So here in this last slide I have is basically we want to illustrate what are the main project phases of Heat4Cool. As you can see, we have started with the development of the retrofitting design planner tool, Tecnalia, Hochschule Lucerne, and Paul Limi were involved in this, mainly involved in this phase. So this phase involved the mapping of the EU building stock, the toolkit data set that, let's say, act as a repository of the technological solution for the retrofitting projects, an optimization of the algorithm for the solution set, and of course the final the final user interface design, which was then later on established. So after this, we moved into the development phase. So the phase 2, this is the actual development of the, let's say, real technology that brought in by our partners. And here we are referring to the solar thermal assisted gas absorption heat pump that was later on installed in Valencia, the PV integrated DC heat pump with the PCM storages installed and commissioned in Chorzów and Sofia, the wastewater heat recovery system implemented in Budapest, and of course the self-correcting intelligent management system, so the so-called SHEBAMS, which is now supported by VAT and Volt. We then moved into phase 3, as you can see, the blue part of this diagram, and so the integration and optimization of the system, where of course involved the simulations, the modeling, the sizing, pilot site level, debugging, and optimization. We finally then move into the last phase of the project, so phase 4, where the evaluation is actually taking place and where we are now. So this phase involved the final engineering and design of the system, the validation, also the publishing of manual guidelines and training material for operating and maintenance of the system. And after the commissioning of the system, extremely important, we are now in the monitoring of the actual data. So obviously there will be energy consumption, energy bills, energy production that will be compared against the planned results coming from the simulation that were previously performed. Then obviously will be used in the final energy audit. So this is exactly where we are now in this phase 4 of the Heat4Cool project. And this is the last slide of my short overview of the project. So here are all the logos of the consortium that you can see, and the contact email address if you have any questions or specific question, or as Serena just mentioned, you can post them directly to her through the webinar. So thank you for your attention, and I'd like to introduce the next speaker that I believe will be Maurizio Zaglio from Sunamp.
Yes. Before doing this, just one clarification. So you can use the questions section in GoToWebinar, in which you can report your questions for the speakers. Please, while you write your message, report also the speakers which you are referring your question. Thank you. So now we can move to the first session of the online training, in which we present the project technologies, and specifically with the presentation of Maurizio Zaglio.
Thank you, Serena. And
The floor is yours.
I guess I'm now control of the slides. Hi, everybody. It's great to be today virtually meeting all of you, and thank you for joining this event. My name is Maurizio Zaglio. I'm currently the International Business Development Manager at Sunamp, and in the next 10 minutes, I will introduce you to our technology and our role in the project. Sunamp it's all about advanced thermal energy storage systems, and in particular what I'm going to present to you is our main innovation to date, which are the heat batteries, so thermal storage system based on phase change materials. And for those of you who don't know what PCM is, I will explain in a moment. The company was founded in 2005 in Edinburgh. It has some subsidiaries around the world, and it focuses on the full development of the technology that we sell. Today, we employ about 60 people, and we are in the manufacturing of our technology as well. And the factory is just in front of our main office, right outside Edinburgh. We also have international partnership with various companies who are offering this technology under their names or under our own names through resale and distribution contracts. Sunamp is active in 4 main fields: the residential one, with direct sales to the end customers, especially in the UK, our home market; the automotive one, where we focus to enhance the performance of both internal combustion engines and electric vehicles with our storage technology; OEMs, where again we mainly work through partnership on the international stage with various companies and key players; and the last, commercial and industrial, where we focus on large scales of systems. In this Heat4Cool project, we are mainly responsible for delivering the phase change material thermal storage and to integrate it to the other components of the system, in particular the heat pump. And I have a slide about that as well. And this means that over the project, we have actually modified and adapted and improved and optimized the design of our storage and the integration of our storage to the heat pump in order to meet those requirements that have been listed by Paolo before in the previous presentation. We are also supporting the installation and commissioning into the trial sites, as well as various tasks in other work packages, going from the dimensioning to the modeling and simulation, dissemination activities, and so on and so forth. As I say, the core of our technology and the big innovation is the phase change material. For those of you that have not worked with PCM before, those are chemical formulations that can absorb, store, and release a large amount of thermal energy by changing phase, which can be by melting and freezing, or by changing the crystallization structure of the material. And it is integrated in an architecture, in a structure, and in a product that is then used to provide useful heating and cooling to the building, as our focus is around residential applications. So in these schematics at the bottom left, you really see how it compares with water. So on the x-axis, you have the temperature. On the y-axis, you have the energy density. And you can see that a PCM, as compared to water, really is really beneficial when it goes above the melting point. A very common material that we use has a melting point of 58 degrees. So it is solid below that, liquid above. And by melting and freezing, it can really store a large amount of heat and then release it to the heat transfer fluid, usually water, to heat up the building or to provide hot water. We are expert in PCM, but we do not sell PCM. We sell the full product, the final product ready to be installed, which of course does not only contain the PCM. The PCM on the top left of these slides is included, and it provides the large energy density. We also have worked a lot on the mean to rapidly exchange this heat to the water, to the heat transfer fluid. So there is a powerful heat exchanger in there. Efficiency is our top priority, and we use very effective vacuum insulation panels in our technology to reduce the heat losses. We have, of course, electronics and sensors to control the charging site and the integration to the other sources and sink of heat in the building. And the same technology can be provided with or without integrated heating elements. When they are present, of course, the benefit is that we can convert electricity into heat directly into our storage technology. And you can see here in a picture what is the real benefit of this technology, which is the compactness. And you see here on the left a standard water-based storage technology, water heater. And on the right, you see the equivalent product from Sunamp that can provide the same amount of heat and hot water as the tank on the left. And apart from this, I've listed here on the right the main benefits compared to water-based technology. I would like to highlight in this presentation the negligible Legionella risk, because actually the amount of water into our technology is very small and just in the heat exchanger, because water is not the storage medium. And secondly, it doesn't require all the maintenance and servicing that is required by unvented cylinders that, as you know, can become quite dangerous should you lose control of the heaters into the water. Again, this is just the same comparison with a commercial water tank with the real numbers attached to it, and you can see that in order to provide the same amount of hot water, we are slightly more than 70% more compact than this water tank. And the big advantage, I've already mentioned, that is also the compactness of the technologies, and our heat losses are 2 to 3 times lower than comparable water tanks. I would also like to highlight here that we have recently received the RAL quality mark from German association RAL that certify that our technology and our PCM-based technology can achieve and exceed 10,000 cycles with minimum degradation. And Sunamp was the first company worldwide to receive this mark A from RAL. We have a standard line of products. We have used various in this project, going from Unique 3 to Unique 80, mainly used for industrial and commercial applications. And you can see in the table below that the storage capacity ranges from about 3.5 to 90 for the biggest product. And you can see also therefore the equivalency to water-based technologies ranging from about water tanks of 70 liters up to almost 2,000 liters of equivalent water tank and storage capacity. These are the boundaries for the project. These technologies, this storage technology can be recharged and discharged in multiple ways through an external thermal source like the heat pump that we use in the project, or with direct electricity, for example, from PV or from grid electricity. The red dotted boundary somehow describe what is included in the Heat4Cool system. So we have a heat pump to recharge the storage. The heat pump is partially driven by the PV electricity, and then it is discharged to provide hot water, space heating, and space cooling to the building. And this is a picture of the technology that we have installed in one trial site. So this is a very advanced heat pump technology that we have developed and that, in close partnership with a French company called Viotherm, that deeply integrate, as you see at the bottom pictures, our storage technology. So the red boxes down there are actually our heat batteries. And plus, wherever it is required, we have increased the storage capacity in the building by adding additional external heat batteries to reach the storage capacity of heating and cooling relevant to satisfy the loads from the building. And this was just a brief overview and summary of our technology and our role in the building. I look forward to your questions at the end of the event, but also feel free, please, to contact me whenever you want to discuss more in the next days, weeks. Thank you very much.
Thank you, Maurizio. So we can proceed now with the next presentation. One second. That's here. Dimos, the floor is yours. Please let me know when I have to change the slide.
Yep. Hello, everyone, and thank you for attending this webinar from our side as well. My name is Dimos Tsagrasoulis. My job position is project manager at the Vattenvolt company, and we are leading the activities for the development of the self-correcting intelligent building energy management system within the Heat4Cool project. I would like to apologize to all of you due to some technical difficulties. I am not able to navigate the presentation myself, so I'm kindly asking Serena to navigate through it. Without further ado, what is the CBEMS system? It has two main functionalities, and it's applicable in two main areas within a building. On the one side, we have the monitoring and control of the centralized heating and cooling generation system, which is the main, let's say, technological aspect of the Heat4Cool project in general. And on the other hand, we are also interested within the apartments to apply automated control in order to satisfy in the best optimal way the end user demand. So, Serena, if you can please move to the next slide. As I stated, two main objectives, let's say, delineate the functionality of the CBEMS system. And these are, on one hand, to enable real-time monitoring of the complete system, and of course its individual components, with the goal of establishing, let's say, the details about its performance, its operational status, and the subsequent functionality that runs in parallel is to allow through the BEMS system to apply optimal automated control strategies, both actually within the premises as well as via remote communication. Next slide, please. So I will briefly discuss the main topics of the CBEMS system, and the next one in this presentation is the control principles. So how did we define which is the best way to operate the system? For this, it is important to distinguish between, as I said, the centralized, the energy production and supply system, as well from the one side, and on the other side, the demand of the occupants. For the optimal use of the heating and cooling production systems, the optimal control principles were defined with the work of the responsible partners as well as the pilot sites were defined after rigorous simulations followed by testing and taking into consideration the different environmental conditions and setups of the pilot sites. So the central system always operate under certain rules that guarantee on one hand the safety of the equipment and the optimality of the use of the system. Now on the demand side, we are exploring the automated application of control logic that that guarantees the comfort of the users, but also the, let's say, minimizes as well as possible the demand that is needed in order to provide energy efficiency. I will come back to this automated control a bit later as well. Next slide, please. This is just a visual illustration of what I was talking about, the automated control. So through the elaborate monitoring equipment installed, we are able to pass to the cloud services the required signals in order to perform the optimization of set points for the different apartments, and these control signals are then communicated back to the individual apartments for applying them for applying the control to the different thermostats. Next one, please, Serena. So now, what about infrastructure? I'm not going into detail about the centralized systems because, as I write in my presentation, each pilot site is more or less unique, and due to the needs and requirements, the solution is very much tailored to the particular buildings. Furthermore, you will see this information in subsequent presentations from the pilot managers. What I would like just to stress that all pilot sites have in common is the multitude of metering and monitoring devices that are installed there, which allow the real-time monitoring and subsequent evaluation of the system. Within apartments, the one common solution was adopted, which is versatile enough to be installed in different premises. Serena, can you please go to the next slide so that so the solution is based on various sensors which wirelessly communicate to a gateway, and this in turn then passes the signals to the through Wi-Fi to the World Wide Web. And allow us to get this and process them, as I mentioned earlier, in our cloud infrastructure. So this system, in tandem to the control logic, creates the basis for the functional operations that I'm going to discuss briefly now as well. So what is the functional pipeline for the automation? The main objective, as in any energy management system, is to perform energy efficiency And in our particular case, our main objective is to, let's say, cleverly handle and manipulate the required demand of the apartments for heating and cooling. So in order to do so, we learn via the measurements the past measurements that we have on HVAC actuation from the occupants, and then coupling that to the environmental conditions, we learn their comfort preferences. And this, since it's a machine learning approach, can guarantee us a consistent and automated manner to do so. These constraints are then comprise an input to a model predictive optimization of the system's set points. And these set points are continuously transmitted to the system for operation, of course, under the requirement that users always have manual control in order to bypass this, from which events we are also learning in order to adjust our, let's say, comfort preferences. So the last slide, please, Serena, is just a visual illustration of the process that I just now reported. So going from monitoring and communication to comfort profiling, and then to optimization, which leads to the automated control. So as a summary, the CyBEM system in the Heat4Cool project tries to, let's say, provide on the one hand all the monitoring infrastructure and the numbers, the values that we need to evaluate the performance of the systems, and on the other side to provide, let's say, an occupant-centric control approach. So thank you very much for your time, and have a good remaining of the webinar.
Thank you, Dimos, for your presentation. Now we can proceed with the next speaker, and will be the last presentation about the technologies involved in the Heat4Cool project. Elisa, the floor is yours.
Thank you. Good afternoon, everyone. I'm Elisa Novak. I work at Fahrenheit, and today I will talk about the adsorption heat pumps, which are one of the main technologies in the Heat4Cool solution. I will start by introducing the fundamentals of the adsorption process, and then I will explain how to implement these fundamentals and build real machines. At the end, I will show how and why we use these machines in the Heat4Cool project. We have only 10 minutes for that part, so please stay focused and note your question for the Q&A session. Let's start by watching some short video. This demonstrator consists of two glass bulbs. One of them is filled with sorbent. The second one is filled with pure water. The bulbs are connected with each other, and in the middle here, you can see a valve. The pressure inside the bulbs is very low. It's about 20 millibars, so we can call it a vacuum. And in this position, the valve is closed. And now we will see what happens when we open the valve. We are opening the valve now. And here, what you can see here is the formation of ice. Okay, so once again, what has happened here? When we opened the valve, the sorbent started to suck in the water and the pressure in the right bulb started to drop. Decreasing pressure caused the evaporation of water and decrease in its temperature, and that's why the water froze. So as you can see, adsorption processes can induce evaporative cooling just as a compressor does in all of the commonly used compression chillers and heat pumps. But what happens when the sorbent gets saturated with water and cannot adsorb anymore? Can we somehow regenerate it? Well, of course, we can regenerate it, use it again, and that process is called desorption. And now I will show you these two processes together, adsorption and desorption, and the differences between them. Let's start with the adsorption. During this process, the sorbent attracts the water molecules. In other words, it sucks in the vapor. At the same time, heat is released to the ambient, therefore we call this process exothermic. After some time, the sorbent gets saturated with water, and if we want to dry it again, we have to somehow force the water molecules to leave. And we can do it by heating up the sorbent. And this process is called desorption or regeneration. Because we are adding the heat, we call this process endothermic. And as you can see right now, the water molecules are expelled from the sorbent. So it means that the water vapor is released and the water molecules are expelled from the sorbent. When we have the regenerated sorbent, we can cool it down and then the adsorption process can start again. And what happens with water? Well, if we want to evaporate it in the next step, we have to condense it, for example, in the right bulb again. In Fahrenheit machines, we use zeolite and silica gel as sorbents and pure water as refrigerant. But in the literature, you can find also other working pairs. For example, activated carbon, methanol. Okay. We already know how the process works, that it gives similar results as the mechanical compressor and regular chillers, and that we could use it for cooling purposes. But how could we build a real machine out of that? There are at least two basic challenges. The first one is how to supply the heat to the sorbent and water efficiently, and how to dissipate efficiently the heat arising in the adsorption and condensation processes. And the second challenge is how to keep this process continuous so that the machine delivers cold all the time. First of all, we have to replace the glass bulbs with heat exchangers. Then, by circulating heat transfer fluid at different temperature levels through these heat exchangers, we can warm up or cool down the sorbent, or we can supply or collect the heat from the water. Typically, we use pure water as the heat transfer fluid due to its very good thermal properties, but I will use the acronym HTF to distinguish it easily from the refrigerant water. Okay, so we have two heat exchangers, our left bulb and our right bulb. One heat exchanger is coated with the sorbent and is called adsorber-desorber. The second one is not coated and operates as evaporator condenser. In our demonstrator, we had a short piping with a valve in the middle that connected the two glass bulbs. In the real machine, we just put the two heat exchangers in one envelope made of thin sheets of stainless steel, and then we put precisely calculated amount of refrigerant water into this created chamber. The envelope has to be sealed very well, because as you remember from the demonstrator, the pressure inside is really low. Any ingress of air will cause a malfunction of our machine. Of course, this envelope is also thermally insulated, and that's actually what we call a module. A module consists of two heat exchangers in one thermally insulated, vacuum-tight stainless steel chamber. And to keep this process continuous, we have to have at least two of such modules working out of phase. When in one module, the sorbent is adsorbing water, in the second module, the sorbent is being regenerated. And that's how it looks in a real machine. We have two finished tube heat exchangers, one of which, typically the bigger one, is coated with the sorbent. In this case, it's silica gel. And the second one, which is not coated. And the heat transfer fluid, HTF, flows inside the tubes. Here in this slide, on the left-hand side, you can see the adsorption evaporation phase. As you know from the previous slides, in the adsorption process, the heat is released to the ambient. Therefore, we need HTF at medium temperature level empty, circulating through the adsorber, cooling it down. On the other hand, the evaporation process collects the heat from the HDF. That's our cooling effect. And HDF at low temperature, LT, circulates through the evaporator. On the right side, you see desorption condensation phase. And since we have to add the heat to the sorbent in order to regenerate it, HDF at high temperature, HT, has to flow through the desorber, warming it up. During the condensation process, similarly like in case of adsorption, the heat is released and has to be dissipated. And here we use HDF at medium temperature again. The main components of our adsorption heat pumps are the process modules. It's always an even number of process modules, so either 2, 4, 6, or 8 of them. Hydraulic group, which consists of pumps and three-way valves directing the HDF at the right temperature levels to corresponding heat exchangers. We have control cabinet with human-machine interface, and of course we have casing with frames. Here at the top, you can see the connections of the three circuits mentioned above. The LT has to be connected to the cold distribution circuits, for example, fan coils. The HT has to be connected with a source of heat, for example, solar collectors. And MT is the heat dissipation circuit. This one may be connected with a dry cooler, wet cooling tower, swimming pool, underground heat exchangers, basically anything where you can dissipate the heat at proper temperature levels. Till now, I have focused on cooling, but it is also possible to use the adsorption heat pumps for heating. All you need to do is to set a corresponding operation mode on the HMI and connect the external HT, MT, and LT circuits a bit differently than for cooling. In the heating mode, the machine's LT circuit should be connected to the low temperature heat source, and MT should be connected to the heating system, for example, floor heating. There are no changes in HT. This circuit should be connected with high temperature heat source as before. On this Sankey diagram, you can see how simple is the energy balance of the heat pump. Heat supplied through the HT and LT equals to the heat dissipated through the MT circuit. Okay, and now when you know what the adsorption heat pump is and how it works, I can explain what is our role in the Heat4Cool project. So this technology is innovative. It's definitely worth further development. That's why we need such funded projects to make it happen. First of all, it uses heat instead of electricity to provide cooling. Then it uses adsorption process, which is less popular than absorption process, but allows the use of lower drive heat temperatures, which makes it perfectly suitable for flat solar collectors for solar cooling. And moreover, the refrigerant is pure water. Pure water is safe for people and safe for our environment. In the Heat4Cool project, we have developed a prototype of a new solar-assisted adsorption heat pump, as shown here in this picture. Our machine is also installed at one demo site, the demo site in Valencia. There, our heat source are solar collectors. We dissipate the heat in the dry cooler installed on the roof, and the generated cooling effect is used for air conditioning with fan coils. And I will not go into details here because I hope you will hear more about this installation during the webinar devoted especially to Valencia demo site. Thank you very much for your attention. I hope I raised your interest in the adsorption technology. Any questions are welcome, and you can also email me for further information if needed. Thank you very much.
Thank you, Lisa, for your presentation. We can now move to the second session of the online training and proceed with the presentation of Pal about the Budapest demo site. 1 second that I give you the control, Pal. Here, the floor is yours.
Thank you. Good afternoon, everyone, and warm greetings from Budapest. let me introduce our site here in Hungary. And first of all, let me introduce myself. I'm managing director of Thermwatt, a Hungarian company owning and developing a technology for the sewage heat utilization that we developed over 10 years ago. And now we use this technology in large scale, especially for large buildings over 10,000 square meter and district level. And here in Budapest, among others, we operate even hospitals. We are the operator of the military hospital of Budapest, which is very important now these days. And this is to tell you that this technology is so reliable that even hospitals can be operated with. So let's see how this technology works. And let me introduce the sewage as heat source. In any cities, we have this heat source around us because naturally using the water, we produce wastewaters that collected in main collectors under surface, under the roads. And the special thing about wastewater is the temperature, which is in every city nearly steady all year round. Means that even in cold winters, when we may have, for example, in Hungary, minus 15 degrees or lower, or in warm summers, what we have maybe 38 degrees or 40 degrees in summer, as far as we are continental weather. So still, we have a very reliable and steady heat source, means that this heat source, the temperature is around 15 degrees Celsius. And once we are talking about efficient heat pumps, efficient heat pumping, we have to talk about water-to-water heat pumps, the most efficient heat pumps. But of course, heat pumps need heat source. And we believe that probably one of the most ideal heat source for heat pumps is wastewater, but we need to harness it. So to use this heat source, we have to have a proper heat exchange. But to manage this, we have to deal with wastewater, which is a mix of different things in a flow, and we have to separate the solids. So, as the first stage in this technology, you will see here, we conduct the flows into a screen, and this screen separates the water. So we have here filtered water. And the screen lifts up the solids, and the solids goes back to the sewer. And we use the filtered water through pumps. We conduct this flow into heat exchanger. And after heat exchange, we feed the heat pump. And once the heat pump heated up, because in heating mode heated up the building, then the cold water comes back through heat exchanger. And after this, we flush back the solids, and the colder flow goes back to the sewer in heating mode. So what happens now, that once we want to heat up a building here, we produce warm energy. In the same time, we produce cold energy. It means that we cool down the wastewater. So in fact, what happens that we use the warm energy of the wastewater to heating up the building through heat pumps, and we do the opposite once we would like to cool down the building. So what happens that we evacuate the warm energy from the building into the sewers, means that we warm up the sewer at that time. The good thing about this heat source is available anywhere in cities. And the special thing about our technology that, as I mentioned, we do this in large scale. As far we know, we have the largest installations of its kind. It means that the installation with raw sewage in town. And we believe there is a huge potential in every city for this. Just to give you an idea, the potential of this technology in a city like Budapest with 2 million inhabitants is roughly 200 megawatts. So the potential is huge. Many buildings can be operated with this technology. So let's come into the detail. And I would like to show you some information about the technology. So just okay, come back again. So as I mentioned, here we have the sewage as heat source. Then the sewage is conducted to the shaft, then we have a fine screen. After the fine screen, the key element is the heat exchange. Heat exchanger produce the clean water in closed circuit to the heat pump, and the heat pump produces, in this case, the warm energy to the building. So in fact, we have 3 steps. First is the screening, then heat exchanging, and heat pumping, as I mentioned before. But let's see how does it work in real, and what are the benefits of this technology. So here with this technology, we save CO2 emission because this is very efficient in heat pumping. But the key is here having a good and efficient heat exchange. Of course, heat exchange in this case, when we deal with sewage flow, is affected by the degree of dirt level of the flow. So it means that sometimes we need to clean up heat exchangers to have proper heat exchange. So the research and development in the frame of this project was to enhance the efficiency of our heat exchangers. They were already good, but we believed that we could do even better. And for this, of course, we have to work also parallelly on the fine screen, because fine screens are made to prepare the filtered water for heat exchanger. So we did 2 things parallelly. We made better heat exchangers, different types, and we made better fine screens, nearly maintenance-free. Because all this has to work by distance, has to work on site without any people, and has to be automized. So we develop here a nearly maintenance-free solution to this technology. And then the problem was in a heat exchange that in the in the heat exchanger we had the sludge that can appear on the surface and the inner part of the heat exchanger. So here we have the screen, and for the screen we developed a cleaning system. It means that we invented here a water cleaning system to release. You can see this part here on to release the sludge residues on the on the screen to have a proper and good filtration for the project. I would like to bring you on site. So let's see what happens here in Budapest. Here we have our customer, which is a municipality, District 4 of Budapest. This is the municipality building. This is the mayor's office. They have also, as there is a state building called government building. They produce passport, ID card, and so on. And here they built a new market hall. So there are basically 3 big buildings built here in St. Stefan Street in District 4 in Budapest. And to visualize better, you may see that the buildings are not so far. And the good thing about this location is there, the blue line is wastewater collector. And this collector, we have a heat source. I will come to this volume, what we have here. And we designed here a heating center to heat up and, of course, cool down the 3 buildings around. If we move to the layout of this site, there we have to double check, of course, the flows, because this is our heat source. And the flow in the summer, for example, of course, it's much lower by night, because people, they don't use their washing machines, dishwashers, toilets, and so on, than in daytime. But we have to, of course, produce heat even nighttime if it's needed. So we concentrate on the low flows also by night, and with some storage, we can equalize this for the whole day. And here we have a daily average of roughly 18 to 20,000 cubic meter days, so roughly 500 cubic meter per hour. coming from a collector here, which is just nearby of our site. So next to this collector, we built a big underground structure. And within this structure, we built a deeper part, which is our shaft with a screen. We put in the heat exchangers, heat pumps, and we connected this to the market hall and also to the municipality and government window. So let's see how does this look like, our buildings. So here you see we have 3 different kind of buildings. One is very old, this is the mayor's office, a completely new one, the new market hall, and the government window. If we compare those buildings, they are very different in size also. Here we have a relatively small, but still 2,600 square meter mayor's office, which was built over 100 years ago. And a relatively new 20 years old government window, and a completely new market hall, which is a big one, 8,000 square meter, also including concert halls, cinema, and other spaces. And then, if we look at the layout of the system, we designed a system. There we have heating central with wastewater screening and heat exchangers and heat pumps on the side that I've just shown to you before. And here we produce in our heat exchangers the closed loop clean water that can feed heat pump. But for the reason to have a better efficiency in transport of the heat, we put another heat pump into the market hall, which is a big consumer in the system. So we have 2 heat pumps, and one is in the big heating and cooling center. Other one is under the new market hall. Here you see the elements. So the first is the screening units. Secondly, then you have the heat exchangers and 2 heat pumps in 2 different locations. And then on the design, you see that here we have very compact design to use under very valuable underground spaces. So we use spaces in an efficient way. And here we produce as maximum energy as we can for this project. You see that the site was existing for operation and was very ideal to put next to the older heat exchanger, the new heat exchangers, very similar in size but very different inside, and compare the efficiency of the new heat exchanger and compare the efficiency of the old screen and the new screen. Once we done the design, we started, of course, the construction, and here we built, we reopened this underground structure, which was under the yellow bricks here in the main square of this district, and then we built in our screen. But before that, we had a shaft cleaning by the operational company of Budapest of Sewage network. And here you see that we opened and rebuilt again this parking, and we built in the new elements of the technology, including the new heat exchangers that you can see here, and the built-in heat exchangers. And after you can see the screens also. The new screens includes, as I mentioned, the water cleaning system, having better efficiency and maintenance-free solution here. And also, parallelly, we developed a SCADA system, a proper SCADA system to this, including the elements where we measure the flows, temperatures, so we can calculate the efficiency of the system, and we collect the data the digital data in computers. The system, once is designed, so this is the new design, is supervised by us 24/7. So we collect all the data, and as far as we are operator, we operate 24/7 this site. And here we see all the temperatures for the heating. This is a heating mode, and all the condition of the heat pumps, and of course also the heat exchange. And we collect those data, and with the collaboration of Polytechnico Milan, with our colleagues there, we evaluate those data, and what we see that we have some result already, because this monitoring started last October. So here we see that the data in some way, for example, this one, I'll just come back here, yes. What we have foreseen, the flow of wastewater and the temperature that corresponds, that it was foreseen. So here you see that from 15 degrees Celsius, the gray line, the steady gray line is that it was foreseen. So it's not exactly 15, but very close to 15, what we have here. And on the orange and red line, you see that after heating, it means that if we cool down the wastewater flow, it's nearly 10 degrees Celsius. That means that as it was foreseen, nearly exactly what happens, that 5 degrees Celsius, we modify the temperature that allow us to produce heat from the wastewater flows. And coming to the end of my presentation, what we have achieved here. So we proved that there's no necessity to provide separate heating and cooling. For example, right now where we have Budapest roughly 18 degrees Celsius, you have seen that this market hall with many windows, we provide the cooling. Whilst we have cold nights and still provide warm energy to the mayor's office. So we can provide heating and cooling even parallelly in this the network coming from the wastewater. And we realized savings coming from the fact that this technology is much more efficient than traditional heating with boilers or even district heating. And we could completely eliminate the use of fossil fuels. Initially, the mayor's office and government window was heated by gas boilers. No, they don't use this at all. And even the sanitary water comes from our technology. Through this solution, we built a very good relationship with the District 4. Even the mayor visited our premises in last February. And now we are part of the very positive communication of this district that using renewables, because sewage is from end of 2018 is renewable, corresponding to the Renewable Energy Directive 2 of the EU Commission. So it's a new energy source, not much use, but it's a renewable energy source that we can use, and we turn completely this district into renewables. So here we prove that we have a more efficient solution in screening, more efficient maintenance in screening, and more efficient heat exchange. So we believe so far, having the data, that we achieved our aims in this Heat4 Cool project. And thank you for the collaboration of the other companies working with us. So if you may have some questions about this great technology, just feel free to ask me at the end, or even having my email here, you can send me an email if you are more interested. So thank you for your kind attention.
Thank you very much, Paul. So we can now proceed with the next presentation from Jakub. Jakub.
Okay. So
Wait a second.
can I have the control? Okay.
Yes, you have now the control. Yeah.
Okay. Thank you, Serena. Good afternoon. My name is Jakub Pluta, and I represent ISNAP company, an engineering consultancy SME from Poland, located in Warsaw. So our company is specializing in energy efficiency and implementation of the new technologies and new materials. We provide also service for business regarding new technologies, and also life cycle assessment service. ISNAP provides in Heat4Cool the demo site building, which is a historical multi-family residential building in Chorzów, which is constructed in 1902. So the building includes 12 residential apartments and 3 commercial premises, which are located in the ground floor. And in the retrofitting process of the Heat4Cool project, only 11 residential apartments have been retrofitted. Individual gas boilers in the apartments are the main heat source for them. So the building is located in Chorzów, which is in Silesia. It is a region in South Poland, and the climate here is continental, with an average annual temperature of 8.6 degrees, and during winter the temperatures can be as low as -17 degrees. Before the retrofitting, there were 4 types of space heating and domestic hot water systems in the building. And in majority of apartments, we could meet a system like in number 1, where both heating and domestic hot water are provided by gas boiler. Another popular system, type number 2, was when space heating was done by gas boiler, but domestic hot water was provided from storage tank with electric heater, or there were few small electric heaters located in the kitchen, bathroom, or toilet in the apartment. Also, there were, for example, type 3, when gas boilers provided the domestic hot water, but apartment was equipped with electrical heating system. In 2 apartments, we met the situation where coal stoves were used for the space heating, and they heated the rooms when they were located, but the electric heaters provided the domestic hot water. So as there were different systems and the building was old, there was need for some modernization to implement the Heat4Cool solution. And in Heat4Cool building, it was in Chorzów building, it was necessary to exchange the electrical installation in common spaces. So here I mean the basement and the staircase, and also in one old apartment. Heating and domestic hot water systems were retrofitted in, as I said, only 11 residential apartments. And as the support for the whole heating system, we installed in the building roof the photovoltaic modules. and the control and managing system was implemented to manage the whole system. The Heat4Cool technologies implemented in the building are 40 kilowatts air-to-water heat pump, heat storage for domestic hot water in form of 8 heat batteries with phase change material inside, and 43 LG photovoltaic modules with solar edge inverter. Regarding the space heating system, we have 2 separate circuits in the building. In each apartment, next to the gas boiler, which, as it was mentioned, is the main heat source for each apartment, we have heat exchanger installed. In this place, both loops are connected. And in the first circuit, which is between the heat pump and the heat exchanger, we have installed the heat meters to measure the heat provided to each apartment. The pipes in this circuit runs through the basement and the staircase to each apartment. The second circuit is internal space heating circuit of the apartment, and it runs through the boiler to the radiators with thermostats, and it returns to the heat exchanger where the water takes the heat from the first circuit. Some modification was implemented in the system which allow for independent work of the boilers and their circulation pumps. The pumps are controlled by the external controller, and this controller also, based on temperatures, control the three-way valves, which was implemented in each apartment, which run the water in bypass to prevent the heating of the water in the heat pump circuit by the boiler. The supply temperature provided by the heat pump to the installation is between 55 to 60 degrees. In case of domestic hot water system, there are also 2 circuits separated by the heat batteries in the basement. So heat batteries have the role of the heat exchanger. They are responsible for preheating of the cold water from the water mains, and the average temperature in the outlet of the heat batteries is around 41 degrees. From the heat batteries, the water runs to the apartments, to the boilers, where it is heated further in case the boiler set point is higher than the temperature provided from the heat batteries. The temperatures in the heat batteries and the charging are controlled constantly by the Siemens PLC. Based on the temperatures inside the batteries, the PLC decides whether there is a need to charge the batteries, and if yes, so then the PLC turns on the circulation pump between the heat pump and the heat batteries. The heart of the retrofitted system is the 30 kilowatts heat pump, which is the monoblock outside machine. The heat pump stands on the previously prepared foundation with gravel filling, which allowed condensate to go to the sewage system, as inside the foundation there is the perforated pipe. The device was transported to the foundation using the crane, as the backyard of the building is a little lower than the rest of the terrain, and also there is a big mass of the heat pump. As it is in a few meters distance from the building and pipes are running in the ground to the basement, we used the pre-insulated twin PEX pipes, like for district heating on the part of the system between the heat pump and the building. The PV system, which was implemented, consists of 43 LG panels, each of power 340 watts, and in total the system gives 1462 watts of power generation. The DC-AC transformation is performed by 15 kilowatts three-phase solar edge inverter, and the installation has around 15 degrees deviation from the south to the west. Also on the roof we installed over 10 lightning protection masts, which secure the PV installation and also the building. ISNAPAS, the building owner, applied to the energy supplier for the connection of the photovoltaic micro installation to the local grid. And in February this year, the energy company has installed a two-way electricity meter to measure import and export of energy. And since that time, the photovoltaic installation is in operation. On the slide, you can see how the PV modules are placed on the roof. Due to the fact that there is a lot of chimneys for ventilation and exhaust running from each apartment to the roof, it was not so simple to design and locate the panels, but we tried maximally use the available roof space. So the self-correcting intelligent building energy management system, shortly SciBEMS, was implemented in the building to collect the data from meters and send it to the database and to control the system. In the building, we can control work of the heating circulation pump, the PLC, which manage the heat batteries, the work of the heat pump, photovoltaic installation, and thermostats in the radiators in each apartment. But the thermostats can be also operated manually by the tenants, the same the set points of the boilers. And if there is a change, the system will adjust to the new settings, respecting energy efficiency. In the scheme, the sensors and connection between the SciBEMS is presented. In the apartments, we have Z-Wave sensors and thermostats for the radiators, and which communicate with the system through Raspberry gateways. The heat meters are connected through wireless M-Bus, and the PV inverter is connected to the internet and to the export and import meter, and it sends the data to the Solar Edge monitoring platform. From both the platform and from all the sensors, the data are sent to our external server. In apartment space, with the help of sensors, we measure indoor conditions like temperatures and humidity. Also, motion sensor can detect when tenants are home to adjust work of the installation. With heat meters, heat distribution throughout the system is measured. For the whole building, we measure heat distribution and temperatures in all hydraulic circuits, electricity consumption by the devices, but also electricity export and import, and the generation by the PV system. With the obtained data, data, we can calculate the efficiency of the system after the monitoring phase of the project. Before the retrofitting process, we performed energy audits and simulations based also on the data from real invoices for energy and natural gas. It was possible to calculate energy needs of the building and its distribution between space heating and domestic hot water. And as you can see, this looks like, based on the calculations, we have 20% of energy needs is distributed for domestic hot water and 80% for the space heating. It was known in the simulations that the electricity needs will not be fully covered by the PV system, but still up till now, during very sunny day, the PV system can cover around 90% of the electricity needs of the heating system. The simulations considered possibility to solve the overproduction to the grid, and as a prosumer, we applied for the connection of the grid, of the installation to the local grid. We can import from the grid free of charge 70% of the power that we exported. So all the simulations achieves the target of 30%, both in savings for primary energy and CO2 emissions. So this is all regarding the presentation of the Polish demo building. Thank you for your attention, and I invite you to give some questions if you are interested. If there will be some questions after the webinar, you can contact me with the email address. Thank you very much.
Thank you very much, Jakub. Now we can proceed with the next presentation given from Michele Pavallo.
Yes, good afternoon. Thank you very much. I see that I have the control now. Good afternoon, everybody. Thank you very much for being here and for attending this webinar. My name is Michele Pavallo. I'm environmental and energy efficiency engineer, and I'm working in Solintel as a R&D project manager. Today, my objective is explain to you and introduce to you our experience in for what is concerning the demo building in Valencia, Spain, and the experience of installing the Heat4Cool system and technology as a solution. As you know, Valencia is located in the western coast and the western shore of Spain. So we have here a subtropical Mediterranean climate. The annual average temperature is almost 18 degrees, so it is warm, I can assure it. And as you can see in the picture, this is the facade of the building we've used for our demo here in Valencia. It is located into the historical center. So we have had some issue for implementing this kind of retrofitting in the building because of the more restrictive Valencian government regulation. But nevertheless, we succeeded, and we have our demo right now up and running. As mentioned in the beginning of this webinar, we are in the middle of gathering information for the post retrofitting for validate and demonstrate our cases. So we are in the swing of this process as well today. So the building has been constructed in 2001. As you can see here, you have the ground floor is dedicated to the shopping spots, shopping center. We have 4 floors, 12 flats, and the total floor area is about 610 square meters. Um, before the intervention of the Heat4Cool technology solution, what we have done here is also, as mentioned before in the previous presentation, we run an energy audit in the building, and what we know is that is the usage of the energy demand as was before it, and we use this figure as a baseline for the future demonstration as well. I forgot to mention that this building has been built for residential usage, and the annual energy consumption is about 61 kilowatt-hour per square meter. That is divided by 54 kilowatt-hour per square meter for natural gas energy demand, and also 7 of them are related for electricity demand. The annual thermal needs are 23 kilowatt-hour per square meter for space heating, 25 kilowatt-hour per square meter for domestic heat water, and 22 for the space cooling. As you can imagine here, since we are in an average of 18 grade degree, also the cooling energy demand is very demanded here in Valencia. So this project solution is very important for this building, but also for spreading this solution in other buildings as well. So we think that this demo will be like very important for the future development, for the exploitability and the marketability of this solution. So what is about the installation? Very shortly, what we have installed in the roof is a solar thermal array, battery of them. This system generates heat fluid, which is pushed inside the three different tanks. We have heat tanks and cold tanks as well. The system is supported by a conventional three air source heat pump, and we have also the absorption heat pump as output of one of the two of the tanks, which is used as we have what was being mentioned in this previously, is used for the creation of the cool that is needed for the cooling demand. Also, this heat is used for domestic heat water and for space heating as well. So the system generated heat and the cooling of the domestic heat water and air conditioning demand. And also the heat and the cold energy are stored in the heat and cooling water tank and supplied for the generation of the domestic heat water gain and the heating and cooling distribution circuit. This is how it works from the technology and the hardware point of view. Sorry, I have, let me see, yes. And we have there the hardware. We have just to introduce what is the system and the software used for control it. Demos has already introduced it, and we have also the same solution in our demos, but very briefly, we have also here the SciDams. The system has, as described, the objective is to maximize the energy efficiency of the system according to the climate situation outside and the demand inside. Everything is controlled considering that we have sensors installed inside the different flats, so we know the situation in there, and also we know the demand of occupancy. And by the Raspberry gateway and the connection by internet and Ethernet, we also have this control of the system, the Heat4Cool system, that which algorithms are used for optimizing all the systems. So the system is optimized every second in real time according to the need and according to the climate situation. So solar thermal array connected to two thermal stores. The solar heat transfer is controlled by the algorithm I mentioned before, and the objective is to maximize the energy efficiency of the system. At the end of the day, the heat, the system controls the heat that could be used for one side for cooling, for example. It depends in the moment of the year and the needs, but also for domestic hot water and space heating. So what was the objective? What is the objective of the project, and which is the status of the energy efficiency we have achieved in the project? Now, of course, before the project, we knew the solar radiation we have here in Valencia. We knew that we had a lot of potential to exploit it using thermal or PV system. In our case, thermal system has been the most important solution. And through the project, our objective was to have at least 30% of renewable energy as an option for our overall building demand, and also demonstrated that the technological solution could be payback in at least 10 years. So what we have analyzed so far, because again we are in the middle of the validation demonstration process, according to the simulation and the data we have gathered, we can assure that the solar thermal system covers still 52% of the heating for space heating and the domestic heat water energy needs, and we can get up to the 27% of the energy demand related to the cooling requests. So we are very much enthusiastic about this number, because if you do the average, we have of course overpaced the 30% expected in the project, and we are in the middle also in the progress of calculating the second pragmatical objective, that is the less than 10-year payback of the technology. So far, we are working to the exploitation and the market analysis. Also, we are waiting and we are analyzing the last figures about technology, but also in our case in Valencia, we are also analyze possible impact and influence could have, for example, subsidy for energy for renewable energy installation in building coming from the Valencian region, for example. According to the first estimation, we think that this number could be achieved. Still, we have to hone and to hone the final analysis to be sure, but we are confident that we can achieve them easily. So as said, we are still in the process of the validation. What I suggest everybody is to follow us in the media and to see in the media and also in the socials to see which is the final figures and the final objective we achieve and we reach here in the Heat4 Cool. And also if you have any question related to the Valencia demo, but also other question, I'm very I'm here. You have my email and you can contact me or the coordinator for any issue and question. Thank you very much for your time, and I'm still here for any question.
Thank you very much, Michele, for your presentation. Now we can proceed with the last presentation of the Heat4 Cool demo site. Emil, the floor is yours.
Hello, everybody. My name is Emil Vitanov. I am the representative of the Bulgarian company Balkanica Energy PLC, and now I'm pleased to present the project Heat4 Cool, designed for the pilot site in Sofia, Bulgaria. Our company main subjects are related to the development and implementation of projects in areas such as waste treatment and recovery facilities, wastewater treatment plants, renewable energy sources, and improving energy efficiency.
Wait, I can put you in the second slide. Yeah.
Oh, the second, yes. So the pilot site in Bulgaria is located in the Bojana neighborhood of Sofia, the capital of Bulgaria. The demo site is a two-floors multifamily apartment building that was completed in 1974. In 2004, 2004, excuse me, a total renovation was conducted and new part was added to the building. It has been continuously inhabited throughout its whole lifespan, currently by 4 families. The building had been designed to have a total of 6 apartments on 4 levels, 2 on each floor. Throughout the years, some of them have been combined into separate habitations. Total floor area is approximately 560 square meters. Additionally, there is a heated semi-basement, an open terrace on the last floor connecting to the central staircase. The roof is mostly flat. The building is with refurbished envelope and exposed facades oriented towards southeast and southwest. Some words for climate. Sofia, the climate is continental with cold winters and warm summers. The relatively low latitude, which is the same as Central Italy, is offset by the position in the Balkan Peninsula, which is exposed to cold waves from Russia, as well as by altitude. The city is located at 550, 600 meters above sea level. Here under, you may see the average temperatures. Maximum temperature 31 degrees Celsius, average temperature 10 degrees Celsius, and minimum temperature minus 11 degrees Celsius. Of course, the building is equipped with a gas boiler for space heating and hot domestic water. On your right side, you can see the natural gas consumption, which is measured 128 kilowatt hours per square meters, 26 kilowatt hours per square meters. Some problem. Okay. So the heating, ventilation, and air conditioning system will consist of 2 electric heat pumps, PCM, protection circuits model heat battery unit, and a photovoltaic system. Centralized heat pump system was chosen because of the higher efficiency and lack of space inside the apartments to put a heat pump in the boiler. The heat pump of 10 kilowatts will be provided, is provided by Heat4 company, and it's directly connected to the PCM storage. The heated water is drained through a pipe system to 2 gas boilers. The heat pump unit is installed at elevation minus 2.40 meters. 3-phase change materials, also called heat battery, installed in the vicinity of the heat pump unit. After the heat pump unit, 2 thermal loops are formed, one of the heat batteries and the other to the heating system. Circulation to the thermal circuit for the thermal batteries will be performed via circulation pump. Circulation pump 1 is indicated. Circulation to the heating circuit will be achieved by means of second circulation pump, which is named circulation pump 2. Only one circulated pump will work at a time. Priority will be given to heat. Priority will be given to heat of the heat batteries through a circulation pump, circulator pump 1. And during the heating season, after the heating batteries have been charged, Circulation pump 1 will shut off and the circulation pump 2 will be turned on. The pilot building is divided into 3 thermal zones. Each of them is served by a separate gas boiler and is also linked to the heat pump unit. Thermal zone 1 includes heated rooms at elevation minus 2.40 meters and elevation 0 meters, as well as the staircase. The gas boiler for zone 1 is located at elevation minus 2.40 meters. The heating system for the zone comprised of radiators for elevation minus 2.40 meters and for elevation 0 meter floor radiant heating and fan coils for floor installation. Thermal zone 2. This thermal zone covers the central and western part of the building elevations, which is plus 2.70 meters and plus 5.50 meters. The gas boiler for zone 2 is located at elevation plus 5.50, and the heating outlets for this zone are radiators. Regarding the zone 3, this zone includes the eastern side of the building at elevations plus 2.70 meters and plus 5.50 meters, as well as elevation plus 8.55 meters. The boiler for zone 3 is located at elevation plus 5.50 meters. The heating outlets for this zone will be underfloor heating. So for each heating zone, the following facilities will be installed in vicinity to the gas boilers. Two-way spherical on-off motorized zone valve implements the connections between the heat pump and the heating outlets for the given heating zone. Hydraulic separator provides the hydraulic separations between the heats. Hydraulic separator, which provides for hydraulic separation between the heat pump and the heating outlets for the given heat zone. Three-way spherical on-off motorized zone valve directs domestic hot water directly from the heat pump to the occupants, or redirect the domestic hot water through gas boiler to be heated at a desirable temperature. Some problem with the slide. Oh. So on this slide, you can see the work performed so far on the retrofit project in the building. These are modernization of the space heating system in one apartment, added new piping infrastructure to accommodate the new equipment and more complex heating cooling system, installation of the photovoltaic system on the roof of the building, started implementation of the self-correcting intelligent building energy management system. The implemented technologies are 10 kilowatts air to the water heat pump, heat batteries based on phase change materials for hot water preparation, 3 heat batteries, each of 12 kilowatt hours, 36 kilowatt hours in total. Photovoltaic system on the roof of the building, 22 LG total generation of 40.28 kilowatts peak capacity.
Do you want me to change your slide?
No, it's okay now. It's okay now. On this slide, you can again see the heating system with its main elements. The main source of the heating power, gas boilers, 2 for the whole building, as it's mentioned above, plus 2 heat pumps, heat distribution in the apartment through radiators with thermostat. It's difficult to move the detached slides.
Yeah, I can do it. So we were here.
The next one, please. Yes, thank you. On this slide, you can see some of the components of the space heating system, part of the pipe infrastructure and a box in which the 2 valves are housed. We focus on 2 of its main features: independent work of the circulation pumps and boilers in the apartments. The valves and circulation pumps are controlled by a separate controller. The next one slide, please. The main characteristic of the hot water preheating system, are displayed here, namely heat batteries connected, 3 in series, heat pump and domestic hot water circuits in a Teckelman system, charging of the heat batteries controlled by Siemens PLC, managing the circulation pump based on the data from temperature sensors in the heat batteries. In the pictures on the right, you can see basement heat pump and the heat battery situated right next to it. A photo of the controller can also be seen on the left side. The next slide, please. Thank you. Here you can see how the heat pump, the measuring heat pump above is installed. The 10 kilowatts heat pump is 1 unit device for indoor use. Connection to the building with pre-insulated cross-linked polyethylene pipes. The next slide. Thank you. So this slide shows a diagram of the energy strings of the photovoltaic system. Each string is represented by 40 photovoltaic panels. For each individual string, we have 1 inverter of 6 kilowatts, which is connected to electricity meters measuring the generated electricity. The next slide. Yes, thank you. The solar photovoltaic system is 12.54 kilowatt peak capacity, comprising 42 LG modules. 33 modules are mounted on the southeast facing sloped roof, and 9 modules are mounted on the flat roof areas using Renewso mounting clamps and A-frames and fixed Cusick hand bolts secured to the roof substructure. You can see these models on the next slides in the picture. Yes. Some words about the solar photovoltaic system. 2 solar edge 6 kilowatt inverters will be used to convert all power from direct current to alternating current to allow maximum possible generation from the system and enable all power to be used for either the heat pump, rest of the building, or to be exported depending on the present demand. The Solar Edge P500 optimizer system will facilitate much greater power generation from the system compared to either string inverter or direct DC, direct current power system, due to the heavily shaded nature of the roof and the limited range which the heat pump can't receive direct current power inputs. The set inverters are to be connected to the internet and the monitoring platform. Two-way electricity meter will be installed by the energy supplier. Besides, lightning protection will also be provided on the roof. The next slide, please. This slide shows the intelligence system, self-correcting intelligent building energy management system. These are the intelligence system, which is represented by a main server through which the individual trackable parameters and monitor it and control it. These are energy consumption, including electricity and heating, inside parameters, including temperature, humidity, occupancy, and illuminance, outside parameters that include humidity, temperature, irradiance. In this way, the main server can control the thermostatic valves receiving data from the respective temperature sensors. This intelligence system includes also a setup monitoring platform, which monitors the photovoltaic energy generation, and Sunamp remote control, which controls respectively the heat pump unit and the PCM storage unit. The next slide. Thank you. This slide shows the monitoring system tracking the data in the apartments and in the building. Monitored data in apartments are listed. You can see them. Indoor temperatures at each thermal zone, humidity and movement, heat and temperatures provided from the heat pump and from the gas boiler to the space heating system, and from the gas boiler to domestic hot water system. Monitored data in the building are heat and temperatures provided from the heat pump to the central heating system, to the heat batteries, and from the heat batteries to the domestic hot water. Electricity consumption by the heat pump and circulation pumps, electricity generation from the photovoltaic system, solar edge inverter, electricity export and import, solar edge energy meter, solar radiation, external radiation sensor, external temperature, the heat pump's temperature sensor. And the last slide. Thank you. As a generation, we can say that the simulations of these retrofits projects show that we can achieve a 30% reduction of electricity consumption, as well as reduce carbon emissions by 30% respectively. With the planned partial sale of part of the generated electricity, we can recoup the investment in the projects, so name it break-even point, for about approximately 10 years. So that was in broad outlines the presentation of the demo site in Sofia, Bulgaria. Thank you for your attention. I remain available for any questions, inquiries about our demo sites. Thank you for your time.
Thank you, Emil, for your presentation. Now we can proceed with the last session dedicated to the questions collected from the audience. I would like to start with some questions for Maurizio Zaglio from Sunamp. So, Maurizio, I will unmute you. Perfect. So we received these questions for you. The first one is, what is the type of heat exchanger that you are using? And what is the store compactness of the store?
What is the second part of the question? What is the
compactness
of the store?
Compactness, yes.
So the heat exchanger is a thin pipe heat exchanger. We can offer it in two versions with a single hydraulic pipe inside. So the same fluid is used for charging and discharging, or with two separate set of pipes inside, meaning that two different fluids can circulate into the storage without being in contact at any point into the storage. For example, one can be used for charging, the other one for discharging, or they can be connected to different services. The compactness, I think I've shown it a comparison in my slides that shows a commercial water tank, and our storage with the same storage capacity is 70% more compact, so smaller than that. Of course, if this person wants to contact me directly, I can share the exact data and size and so on.
Perfect. And another question for you. What is the commercial status of your heat battery?
So we reached commercial stage with the first product in at the end of 2014. So we are currently at the third generation that was developed during this project and that we use in this project. And it's fully available in the UK. And outside the UK, we work with partners, distribution partners and OEMs. So again, I'm happy to share more details to those people that wants to understand more about their availability in their countries, and we can either supply them direct or through partners.
Thank you very much. So we can now proceed with Michele Bavallo and music.
Yes.
Perfect.
Do you hear me?
Yes, we can hear you. So the question is, what technology or process do you think will contribute the most towards energy efficiency in the next 10 or 20 years? And what technology do you think needs to be prioritized in research?
Yeah, well, it is a very market
broad question.
Yeah, broad question, but the answer would seems like the easy one. I mean, the best technology is the one that with which we can reach the most efficiency, the most efficient we can get according to the technology limits. And of course, it is we have from one side the performance of the technology, from the other side the cost. So I think that as law of life, I mean, the best technology has to accomplish with this, at least with these two target and these two perspectives. For what is related the name and surname of technology, we have seen here different solution, and I think that we can consider this solution like from the general point of view, the one that should be also pushed as well in for the future. We have to understand that this project is not TL9. I mean, this technology have been thought to be like a prototype for this building, for this project. And for me, if we are able to multiply in the market this technology the day after, we will also have the opportunity to decrease the cost of them, and it would also help us positioning this technology. Now, the technology name are the one we have seen. For me, we have a lot of opportunity there, but also it is not it's not like talking about each technology individually, but also a blend of them. And for me, according to my personal previous experience, the solution is in the blend. I mean, the solution is try to put together the best solution technologically, but also the best solution according to what is needed. Because sometimes, talking with the European Commission, sometimes we have this, we receive this question: why all the solution that this European project bring to the market have not stay there, and nobody is going to bet on them? Because The issue is not only the cost, but is that each technology is sold individually, and sometimes the blending is the best option according to, for example, different situation. If we talk about Spain and Valencia in the specific, because Spain is a big country, we have here the same. If you have seen my presentation, we have the same interest for heat and then for the cooling. So if you think about that, it means that both technology could have an each home market here. So, and if you consider the north, in which you don't have that much, for example, of energy radiance, you have to go for another blending of this technology. Also, not only the technology from the real technology system, but also the software, all the system related to software and the hardware that we've talked about. I think that the algorithm is also the future. Algorithm that has to be owned always more, even if here we have a very good solution, but I think that this algorithm has to grow along with this symbiosis of technology I've explained before, this blend. And once we are honing this process, in each iteration, we will get a better solution. I hope that I have answered this question. I know that I cannot say, name as a name of technology, but at least from the philosophical point of view, I think that maybe the question is satisfied.
Yes, and I have also another question for you. So does the system supply that is running in the Valencia demo site supply also the heating and cooling at the same time?
Yes, I received an email. I think it's Patrick here. I was about to answer to him. Yes, of course. You have to consider that we have three deposits, two heating deposit and one cold deposit. And for example, if you have different system for domestic heat water and also for space heating, of course, having two pipeline, I would say you could switch one, for example, cold and heat, or double cold or double heat, for example. It depends. And of course, yes, the answer is yes, of course. And it is very much related to the system, how the system is configured. In this case, you can do that because the system are different. The pipeline system are different. If you, for example, consider that you have just one pipeline for cooling and heating, for example, the space heating, in that case, you don't, and for example, the system is related, for example, going through the domestic heat water, you couldn't do that. And for this reason, we have doubled the pipeline for having this option and even improve the overall system in terms of efficiency and cost effectiveness. I'm not going to answer the email because I think I did here.
You already answered here.
Thank you, Patrick.
Now, I have a question for three speakers, namely for Maurizio, Pal, Elisa. So the question, and we can maybe switch to one speaker to another, one by one, to receive your answers. So the question is, the PCM storage, adsorption device, sewage heat source, these are alternative technologies to much more common technologies, respectively, hot water storage tank, heat pump, geothermal heat source. How do the new technologies, so your technologies that you have proposed to us today, compare in terms of performance, cost, and reliability? What is their main added value? We can start from Maurizio and then go to the other speakers. Maurizio, let me see. Can you unmute yourself?
Can you hear me?
Yeah, now yes.
So PCM thermal storage compared to water-based storage, so water cylinders, performance-wise, they are better. So we really work hard to make sure that high flow rates of hot water is delivered from the compact products. and the heat losses are much lower than water tanks that are out there in the market, and therefore we have an overall higher efficiency, better energy label, and so on and so forth. Then I think the second part of the question was about
what
the cost.
is the main added value of your technology?
Main added value is around, of course, the flexibility of installation. We require much less space to install this storage, so we can provide the benefits that storage can bring to a building, a thermal storage can bring to a building, to a much wider market. Think about, apartments in London, where the surface space is very expensive, and therefore there is a big incentive to use compact technologies, and but still it gives you the as I said before, the possibility to add the storage to your building. And second part, I would say it solves other issues, the Legionella one I've mentioned during the presentation. And a water tank, everybody compares our product to a water tank, but in reality, a water tank requires quite a lot of ancillary components as well. When you install them, expansion vessel, pressure and temperature release valves, and so on and so forth. So overall, also from the economic point of view, if you compare installed prices, we are already quite close to high quality cylinders today.
Thank you. So we can now go to Elisa.
Yes, of course.
Do you remember the question?
Yes, the comparison between the state of the art, the conventional heat pumps, and our heat pumps. Okay, so first of all, our heat pumps use waste heat. It can be waste heat, it can be solar heat, it can be heat from the processes. So it increases the overall energy efficiency. It also consumes up to 90% less electrical energy because it has no compressor. In our machine, the only consumers of the electrical energy are water pumps, which usually consume less energy than compressors. And we also have the controller, but the energy consumption of the controller is marginal. Our devices are also robust. They have very simple constructions. There are no moving parts inside the modules, which are the core of the unit. If there is a problem with a pump, it can be easily exchanged without the need to get inside the whole the machine and destroy it. Or so the maintenance is. It doesn't. Our machines don't require very a lot of maintenance in the meaning that when you have the compressor, you have to check it regularly. When you have synthetic refrigerants, you also have to do the checks regularly. With our machines, there are no synthetic refrigerants. We also have no overpressure because the modules work under vacuum. And there was also a question about the costs. Our machines are a bit more expensive than the state-of-the-art chillers or heat pumps, but we are able to achieve attractive payback times, especially with the subsidies. Like in Germany, we have BAFA, for example, and in other countries, I'm sure there are also attractive subsidies available. And maybe one other advantage, I don't know if that's the best one, but our machines are also silent. Without the compressor, they don't make much noise. So that would be the answer from my part. Thank you.
Thank you very much, Elisa. We can go to Pal. So he can answer to this question. Pal, can you unmute yourself? because I
Okay.
cannot. Okay, now yes.
Here I am. Sewage heat or wastewater heat recovery. The key thing here is the efficiency, because we have a very good heat source, and this heat source is available nearly everywhere in cities. This is a large city solution. So compared to other solutions, depending on the temperature, for example, in heating mode, if we heat in low temperature like 30, 40 degrees, we have a COP above 6, for example, this hospital that we operate, which is very high compared to other solutions. And also, this solution is considered no renewable and green solution. And another thing, if I come to the added value of this technology, that we experience in many cases that we can upgrade the size of this technology. So we may start with 1 or 2 buildings, and then we have several buildings around because of the efficient heating and cooling. So here, the size of heating and cooling center depends only the wastewater flow. And the good thing here that we can check this in advance. So comparing, for example, for geothermal solutions, that it's difficult to foresee exactly what happens. Then here we can know exactly in advance because we can measure the flows in advance, even the daily flows and all the details of the flows, because it's an existing flow, easy to measure. So we can make easily calculations in advance and to model in advance what will happen in this system, which very efficient compared to other solutions.
Thank you, Paul. And I have another question for you. So, can the sewage technology be used in different nodes of the same sewage network? If yes, how would the efficiency of the heat pumps at those nodes might vary?
Very good questions, because as far as we are dealing with heat pumps, water-to-water heat pumps, so we have a condenser and evaporator, so we have a warm and cold side in the same time. So the answer is definitely yes. We can operate, and we do operate warm side heating and also cooling at the same time. Once we do this, easy to understand that one is free, because for example, right now we turn the system into cooling mode, for example in Budapest, in this presented project, and in this cooling mode we provide cold energy for mainly for the large building of the market hall, but the warm energy, instead of losing this and put this into the sewer, we use for heating the mayor's office. So it's an addition again. So if we add all together, we can add on COP. So theoretically we can achieve COP 8 and 9. So very high efficiency. So to understand that from 1 kilowatt hour of electricity, we can produce 6, 7, or 8 kilowatt hour of heat if there parallel heating and cooling in the same system.
Thank you very much for your answer. We can now proceed with the last question that we have for Jakub, since we're already running out of time. Jakub. So the question is, why you didn't opt for a more powerful heat pump, thus to exclude the gas boilers from your system in the Horzow demo site?
So in accordance with the project assumptions, we tried to make the best use of the existing infrastructure. So to use the existing gas boilers as the main heat source and provide the heat pump with as a support for the system. Also, bigger. Even using this 40 kilowatts heat pump, we had to retrofit the electrical installation of the whole building, as it needs a lot of power to even start up the heat pump. and bigger heat pump will also means bigger costs. So to consider the energy efficiency and one of the goals of the project, the payback around 10 years, we tried to, as possible, minimize the cost of the overall retrofitting process, and to not replace anything with the new system.
Okay.
So I hope I was able to answer to this question.
Yes, thank you very much. So now we are at the end of this first online training. You will receive all the presentations in the upcoming days, and if you will have any other questions or you want to ask for clarification, you can email the speakers. And please feel free to follow the Heat4Cool project in all our social media and website. Thank you for attending this online training, and have a nice evening. Bye.
Thank you.
Thank you. Bye-bye.